Geometry students, we are in chapter 4 and we are looking at section 4.4, and this is the first chapter where we're going to start talking about ways to prove that triangles are congruent without proving like all their parts are congruent. So today we're going to discuss SSS, which is a theorem that refers to side, 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 and SAS, which refers to side, angle, side. Let's take a look at our vocabulary. So our vocabulary today is really short. It talks about what's called an included angle. Even say this triangle ABC, the included angle between segment AB and segment BC would be angle B, right? So included angle refers to, let's say I had some information about these two angles, or rather these two sides. If I had some information about these two sides, let's say specifically that this side is congruent to this side and two triangles and this side is congruent to this side. If I wanted to refer to a specific angle, one angle I could refer to is the included angle. So included angle basically just means an angle between two specified segments. And we're going to find out in this section that this is actually enough, having two sides being congruent and an included angle being congruent with one another. That's enough to prove that your two triangles are congruent. So here's our first postulate. Our first postulate is called side, 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 forever abbreviated SSS. So it's called the SSS congruence, and what it basically tells us is if I have two triangles and I can prove that each of their three sides are congruent to each of the other three sides in the other triangle, then I know for a fact that not only is that those sides congruent, not only are those sides congruent, but those triangles are congruent as well. So since side AB is congruent to side DE, right, and side BC is congruent to side EF, and then CA and FD are congruent as well. Notice the ordering. And AB is congruent with DE, therefore AB, DE. Notice that they're in the exact same place when naming the triangle and its congruent. So we got to be careful about that. Cool? All right, let's take a look. Take a look at this first example. So this first example is giving us an opportunity to demonstrate our understanding of the SSS congruent postulate or SSS theorem, or from here on out I'll just call it SSS, right? So it's given us an opportunity to demonstrate SSS in this thing called a flow proof, which I have never done with you. And as I mentioned before in a previous video, I'm not really too versed in this. Like, I haven't done it before. It makes kind of logical sense, but so basically I'm going to kind of cheat my way through this. By saying cheat, I mean I've got like under here, I'm going to just like start deleting stuff, and what you're going to see is displayed what's in the textbook. But follow along. I think you might like it as a way of proving things. If you don't use it. You can always use the formal 2-column proof, which I'm comfortable with. Paragraph proofs I'm still a little but sometimes it's easier just to get your thoughts out there and paragraph proof it up. And if you like flow proof, let's rock out with that as well. All right. Now, after my disclaimer, let's discuss what's going on. So we're given some information here, and what we're going to do is prove that these two triangles are congruent. The information that we're given, and I like to always mark my picture anytime I'm given some information. So GH is congruent to KJ, and so I'm going to go ahead and mark that. GH is congruent to KJ, and then HL, that's this guy here, is congruent to JL, so I'll put double marks here, double hatch marks. And then we have that L is the midpoint of this segment GK. So obviously, you know we're going to use SSS. The last thing we need to prove is that GL is congruent to LK, and that's pretty easy because we know by definition of a midpoint we're going to break a segment up into congruent pieces, correct? All right, so you know that that's going to be the core or the crux of this particular flow proof. So the flow proof starts off by giving all the given information. So it says, okay, given this bit of information, given this bit of information, and given this bit of information. So basically a rewrite of each of these pieces are done separately. And what we can do is now use arrows and information to kind of gather where we're going. So these two bits of information leads to, well, I shouldn't have done it that way. Let's forget about this. Pretend you don't see it. Cover your eyes. Avert your attention. Let me do it for you. All right, let's pretend we don't see this yet. All right, so before we figure out where all this leads to, this information leads to the fact that GL is congruent to LK. And notice how they write it in a flow-proof form. They'll write midpoint theorem. They'll write where it came from, right? So it's like statement, reason, statement, reason, statement, reason. And then they just say, okay, all these points, all these concepts, all these bits of information are going to point to this next thing here, which you already saw. But now we see it again, that indeed we've got these two triangles being congruent by SSS. I don't know, it's neat. It's just a way that I've never thought about it before. So I'm just being honest. But maybe we'll rock some flow proofs the next time we see each other. So with that in mind, we get the fact that these guys are congruent, right? Which is what we were looking for. And then we can use SSS to bring it home. Let's take a look at another example. So here we are with example 2. We are asked to do a couple things. First of all, we're going to use SSS on the coordinate plane. You know, when we introduce concepts on the coordinate plane, we're going to be talking about things like the distance formula. Yes, you remember. And so we will talk about the distance formula here. We're going to graph both triangles on the same coordinate plane. And so we've got these two triangles up here. Sorry for not doing this. ABC has these vertices and EFG has these vertices. We're going to graph them both, and then we're going to use our graph to make a conjecture as to whether the triangles are congruent, and we're going to explain our reasoning. And then we're going to write a logical argument using coordinate geometry to support the conjecture that we made in part B. All right, so let's get started. All right, it took me a long time to do this, but here it is, my beautiful graph. And so now we can take a look and kind of compare and see if these triangles are congruent. And there's a couple ways to do it. Maybe you'll dig this, maybe you won't. I'm not saying it's a cheater's way, but I'm just saying it's a way to kind of circumvent the distance formula. You can kind of look and say, okay, if you think about the distance from A to B is going to be we're going to bring slope concepts in here too, so just check it out for a second. Just walk with me. All right, so if I looked at A to B, I can say, okay, from here to here, it's like a box, and this rectangle is 1 over and 2 up, and the diagonal is AB. Does any other segment on this triangle have that same quality, that it's the diagonal of a rectangle that's 2 by 1? I know this seems a little weird, but like if you look at this guy, this is not 2 by 1, this is like 4 by 1, right? Like if you think about the rectangle that this is a diagonal of. So obviously these guys are not the same length. And if I do the same thing here, if I come over here, it looks like this is a 2 by 1. So I don't know if this is making sense. So I'm kind of feeling like, without even doing coordinate geometry, which we will, and when I say coordinate geometry, I really mean the distance formula, I'm feeling like FG rather, maybe equivalent to AB, and maybe EF is equivalent to, I don't know if I use that same rectangular concept that I'm trying to come up with here. Maybe AC, maybe not, because it's 1 over. So this is the way I think you can think through it. All right, so this is just a little bit of logical discussion, but let's go ahead and do the thing that we know how to do. We're going to do the distance formula between each point, each pair of points in each triangle. Okay, so after a lot of work, here it is. I've listed the sides. Oh, by the way, you may have observed I had A here before and then B here, and I had them interchanged, my bad. And so as we look at it, we see that 2 of the sides are congruent, but the third side isn't. So by SSS, we can say that these two triangles are not congruent. All right, I think that makes sense. And we could write a logical argument with this information to support our conjecture. My conjecture actually was that they were congruent because it was kind of looking like it, but now I know the truth. All right, let's go on to the next example. Before we go on to the next example, let's take a look at the next postulate that we need to talk about. So you remember we just talked about the SSS postulate. Now we've got the SAS. SAS is what we talked about a little bit earlier when I said that if you have two triangles and you can prove that 2 of the sides and the included angle, it has to be the angle included. What I'm trying to say is it couldn't be like, let's get rid of this, right? Like, couldn't be like, this is not enough to prove 2 triangles congruent. Like, that's not good. at all. When it says SAS, it means that the first a side, then an angle, then a side. So it's called side angle side, or SAS, and this is not acceptable. It must be exactly in the order that the text says, SAS, all right? Has to be, has to be, has to be. Sometimes I'll tell students, and this is not to be negative, but I'll tell students, if the order of equality, let me do it this way, if the order of equality produces a word that we won't say often, angle side side, right? If it produces an acronym that you don't want to say out loud, then you know you're doing something wrong. So we can say SAS, SAS, that's cool. You're not going to say the other thing, all right? So that's another way to keep in mind that you've got the right acronym or the right kind of idea when you're trying to prove two triangles congruent. So you can prove two triangles congruent by proving that the side angle and side angle side are congruent once those two sides have as an included angle the angle that we're talking about, the angle of congruence. If that's the case, then you got two congruent triangles. Here we have an example that we're going to use the SAS to prove triangles are congruent. The scaffolding for a stage lighting show appears to be made of congruent triangles. So the information that we're given is if WX is here, is equivalent to or is congruent to YZ. So as I told you before, I love to mark this information as I get it. So WX is congruent to YZ, that's this segment here, and WX is parallel to ZY. So I'm going to put little arrows of parallelity, or that's not a word, arrows of parallelness, that's better. I'm going to put that there. Write a two-column proof to prove now that this information is true, that triangle WXZ is congruent to triangle YZX. All right? Because highlighting is awesome. I did some highlighting, and the first thing I'm going to do is, which is a good way to start off, I'm just going to write some of the information that I have. But I should really, honestly, before I start writing stuff down, I need to kind of think through what I'm doing. We know we're doing single side angle side, so we have a bit of a hint. And we're looking at the two triangles. This one I highlighted in yellow and this one in green. And I'm noticing that, okay, they've got these two sides equivalent. Oh, they share this side, so clearly this will be an easy thing for me to say, right? I can easily say that ZX is equal to ZX reflexive property, therefore I got two sides. Now it will be really awesome if we can prove that some angle is congruent, like this angle and this angle, because we get the included angle and we could do a happy dance and say that we've got the thing done. Is there any way that we can get these angles congruent? And that pause is for you to go, oh yes, eureka, teacher, I can. I figure that these are parallel lines cut by a transversal. Alternate interior angles are congruent. That doesn't rhyme, but in my mind it was a rap song. So let's use that and solve. Now my first two statements are just my given information. I'm going to throw out this third one where we say ZX is congruent to itself by the reflexive property of congruence. Then I have number 4, which tells me that angles WXZ are congruent or is congruent with angle XZY or YZX, and that's because parallel lines cut by a transversal means that the alternate interior angles created are congruent. And with that, check it out. I've got my side, my angle, and my side. And so now I can bring it home. Drum roll, please. Just kidding. Triangle WXZ is congruent to triangle YZX by the SAS. Theorem, postulate, idea, whatever. Last thing we'll talk about is this lovely proof that we're going to finish off in another video. But other than that, let me know if you have any questions. Definitely watch the second video. But let me know if you have any questions, and I'll happily answer them for you. Take care.